All right, so now you can hear me. I had the wrong, there we go, Jason. We're good to go. All right, thanks everybody. And we've got in the house, we got Don Gannier, good morning. Felix Sandoval, Columbia is represented. We have Steve, we have Jason. Happy Tech Tuesday to you as well. All right, today, so if you recall, remember, last week we started the discussion around the trip curve, the time current characteristic curve. And I thought this week, what we'll do is we'll springboard off of that and we will talk about the circuit breaker, the molded case circuit breaker specifically. But Wayne Janik, thanks for joining. But thank you so much for that sound check, buddy. I had the wrong cam link. I'm mobile today. I'm traveling. Got little Maggie in for surgery today. She has a torn ACL, so they're going to start surgery around 2 o'clock, something like that. But I'm in Columbus, Ohio, so got a hotel room and waiting for that to get done. So in the meanwhile, the show must go on. So we're going to talk circuit breakers, and we're going to get down to basics. We're going to understand proper application, and I want to share with you an industry reference that I think everybody should have on their computer. Let's talk circuit breakers, and it all starts now. All right. Thanks, Jason. Yep. I think. Well, I know Maggie's in good hands. Came out here to Ohio State University. They've got a great veterinarian clinic, and they've got a good doctors. Some really good doctors out here. So she will do, I'm sure, very fine. But we got about 2 months, or maybe a little bit more, of recovery time for good old Megalodon. So, all right, we got Vinny B in the house. Can't go on without Laurel. So Laurel from Omaha, excellent. Hopefully we get Robert from Omaha. You know, Laurel, I haven't seen him in a little bit. I had a text from him the other day, but hopefully he's doing well. And we got Jason Doty in the house. Thank you, Jason, for joining in. We've got Steve. We've got Felix. Yes, 489. Looking forward. We're going to have a good time. I think we're going to have a good discussion on this one. And here's what I want to do is, boom, man. I tell you what, I'm having some difficulties here. There's that one. And I should have a dialogue. Let me get this. I'm mobile, so bear with me. Boom. All right. So bear with me here. I got that cam link. This cam link is, let me unplug this and plug it back in again. Hopefully I'm still on. All right. So my cam link 2 is a no signal. And I just had it working. So anyway, the document I want to share with you, if, geez, oh man, close this out, bring this back open. Okay, so there we go. Now we're working. I don't know if we are or not. We were. There we go. Okay, so here is the document that I want to share with all of you. After a little bit of a technical difficulty, I've got NEMA AB3. So the NEMA AB3 document is, I think, something you should have in your library. It's the molded case circuit breakers and their application. It's a document that's put together by NEMA. It is through the ANSI process, so that's a good thing. This one here was published July 22nd, as published July 22nd. No, this is 2013. Where's the publication date? There it is. Oh yeah, July 27th, 2023. So it was approved and was published February 20th, 2024. So it goes through the ANSI process, meaning there's a committee, meaning it gets public review and all that jazz. Remember, the ANSI process is what we use even in the NFPA process and other codes and standards. It's it's used to ensure the process is followed and we get good public review and we have a balanced committee and all that jazz. All right. So let's do this first. If you think about a circuit breaker, let's look at the definitions. Let's look at this is the scope of this document. We're going to talk about rated voltages up to and including 1,000 volts AC, AC or D and DC. I have a rating of interrupting ratings up to 5,000 amps or more. And okay, so here is a good one. This is a good note right here. Consult the manufacturer for DC only or 400 hertz circuit breakers. Remember, your multi-case circuit breakers are typically listed and evaluated for 50, 60 hertz. 50 hertz for our close brethrens in other countries, 60 hertz here in the Americas and in U.S. and similar areas around the U.S. So, but 400 hertz presents a challenge because of the higher frequencies. You need to make sure that your overcurrent protective device can handle those higher frequencies. And there are industry reference information from the manufacturers to help you understand how to properly apply overcurrent protective devices at these different frequencies. So it's important. Frequency matters, and it's important to understand how the product is listed and it's tested. There's your 600 volts. Wherever the abbreviation UL appears, it shall be understood to mean Underwriter's Laboratory. So that's your UL standard that we're evaluated to, and that's UL 489. I believe Steve or somebody had mentioned UL 489. Hey, Lou Petrucci, we got Lou. Hey, we got the Hofkenmeister in the house, and thank you. I'll give you guys an update later on this week, probably Friday. I think I'm going live on Friday, and I will share some of Maggie's results. I'll have to be in probably the kitchen and close to where Maggie is because we got to keep her activity down. So anyway, references. I'm going to walk through this document, and you can download this. I'm going to see if I can. Let me see. Can I? If I bring up my web browser, it does not bring it up. For some reason, it does not bring it up. Let me close some of this stuff. Edge, Outlook. I can bring up Notability, and it will work. So if you know what I'm going to do? I'm going to do this. I'm going to put in the chat. I am going to put in the chat a link to NEMA AB3. And so what you can do is just go to your search engine and type in NEMA space AB3, and you'll find the link. Control C, and I'm going to bring it back. And I'm going to put it in the chat for all of you out there, I believe on YouTube. Hey, Jason, no NTI this year from me, buddy. I wish for a few different reasons, they weren't doing a 70E class up there, so no need to be there. And we weren't doing Codes and Practices 3 and 6. So we do have the trade show Saturday and Sunday. So hopefully, I'm probably not going to be there. But Kevin Arnold and Jerry O'Connor and all the guys from Eaton, and I'm sure other manufacturers, ABB, Schneider, etc. They're all going to be there at the trade show. So get over there to the trade show. So I put the link in, and I believe it. I don't think it goes out to the LinkedIn site. I think you got to go over to YouTube site because I don't see the link in the from a LinkedIn perspective. So in any case, that document you can download that for free, and it gives you a lot of the good references. Now, a circuit breaker. Can I call up? Man, I'm not sure why. Let me try to call up a different browser. Not sure. Let me try closing this puppy. Hey, Joe Bellantoni in the house. Good to see you, my friend. All right, so I can't do that. All right, so in any case, you guys can go out to NFPA link and take a look at the at NFPA link some of the defined terms. But let's take a look at what. Hey, there you go, free download. Absolutely, yeah, and the NEMA. I guess you do have to create a NEMA account. Similar to NFPA, but it is free. It is free. Okay, so a circuit breaker. Let's take a look at this definition right here. A circuit breaker is a device designed to open and close a circuit by non-automatic means, and to open the circuit automatically on a predetermined overcurrent, and that's that trip curve that we looked at last week. Remember, last week we went over time current characteristic curves, and we showed circuit breakers. We also talked about fuses. We should have talked about relays too. Maybe I'll make a whole nother session just on relays. But the automatic nature of opening on a predetermined overcurrent is dictated by the TCC curve. Okay, that's the time current characteristic curve. That's what determines, I call it the resume of a circuit breaker. That's basically tells you how it's going to perform when current passes through it. It's either not going to trip if it's low enough, or it's going to trip, and the amount of time that it takes depends upon the amount of current that is passing through the overcurrent protective device. All right. So, and just like all electrical equipment, when it's operating within its proper application, you do not want damage to itself. Okay. Within its rating, you don't want it to damage itself. You don't want it to achieve an unintended rapid disassembly in the field, and you don't want it to overheat and melt down, okay? So proper application of the overcurrent protective device is a critical piece of the puzzle, and that 400 hertz discussion that we just had, one of the pieces of the puzzle. There are so many different pieces of the puzzle. It's important for us to understand the proper application of an overcurrent protective device, whether it be a circuit breaker, a fuse, whatever it is, regardless. We need to understand the proper application and all the different parameters. I'm going to filter down through this document because what I like about this document is it puts things into perspective and it helps identify some of the key parameters from a NEMA perspective. So one of the things you got to think about is when you think about these types of documents, a NEMA generated document like this has gone through an ANSI process. Guaranteed, Eaton, Siemens, ABB, Schneider Electric, probably anybody else, Passon Seymour, Hubble, a lot of individuals were around the table when this document was developed. It had to go through NEMA codes and standards, and it gets a rigorous technical review. So what I like about this document is it gives us a perspective from a NEMA perspective on circuit breakers, specifically molded case circuit breakers, and you've got to think about the scope of the document as well. All right, so we know what we're dealing with with a circuit breaker. It's going to automatically open based upon its time current characteristic curve, and I need to be able to manually open it at my discretion. Okay? All right. So there's different types of circuit breakers. I can have GFCI technology built in. I can have surge built into it. Ground fault protection of equipment, I can have that built in to the overcurrent protected device. We could shunt trip the circuit breaker as well. A circuit breaker is going to be in an enclosure. It's going to be installed on a bus, typically put in an enclosure. Circuit breakers incorporating ground fault protection of equipment. We already said that. We already said we can do that. CTL is, okay. Prevents more circuit pulls. Okay, so I'm trying to in my mind trying to think of how do I say this. So sometimes you might have twins circuit breakers and whatnot. There are types of circuit breakers that basically prevents more circuit breaker pulls from being installed than the number for which the assembly is intended and rated. Now, in the past, remember we limited it to 42 circuits because we always had the 42 circuit panel boards, etc. That number, that limitation was removed a while ago. Oh my goodness, I can't remember how long ago it was, but it was a while ago. Now I can have a panel board with as many circuits as I'd like, but that doesn't mean that I'm not going to design a panel board that has a limited number or a capability. So what I like about this what I like about this discussion is it points out the fact that your circuit breaker and your equipment that you're going to marry it with, whatever you're going to put it in. I always say, I'm going to put it into a big gray box, the gray box. You're going to put these devices in an enclosure, and they have to be able to match with each other. Not only the form factor on how to either plug or bolt or connect that circuit breaker onto the bus, that has to be in concert and listed and tested as a pair, but also other aspects of it. Temperature rise, heat is a big issue when it comes to equipment. Temperature rise inside of electrical distribution equipment is, I would say, arguably one of the most difficult tests to pass when it comes to standards and development. Oh, thank you, Dawn. History, baby, right there in the 2005 code. I believe you're right that was probably came out in the 2005 code. No open panel boards on slate. Yeah, you know what, Jason, here's the thing. Think about the cost reduction we can do if we did that, huh? We could make the electrical installation so much less expensive if we just get rid of all that steel. Now, slate could be kind of hard to get to, but why not plywood, right? I mean, give me a break. Anyway, I digress. Okay, so close open operation, common trip. Okay, so this is an important one right here. Let's watch this. I can go like this, and then boom. So common trip circuit breakers. There's a difference between putting a handle tie on two circuit breakers so that I can open and close them, or a circuit breaker that ships from the factory that may have a handle tie built in that indicates that it is a common trip. What that means is both poles will open at the same time, or three. In some cases, you might have a three-pole circuit breaker. All three poles are going to open at the same time as a common trip. if I have a circuit breaker and I put a handle tie on, or it comes from the factory with a handle tie, and it's not identified as a common trip, then that means I'm a common disconnect. But each pole will trip independently of the other. I could have, if I have a 2-pole breaker, I may have, like say it's a shared neutral application, I may be able to trip one of those 2 poles and the other one stays on. But when I turn the breakers off, I'm going to turn them both off because I have the handle tie that's going to turn both breakers off and then both breakers back on again. And there's a requirement in the code for shared neutral applications where I need to make sure that I can turn both of those circuit breakers off, but it's not a requirement that they have a common trip. All right, so it's important to understand the difference between a common trip and turning both breakers on and off. I don't know what I would call that, common control or whatever. Selective coordination, I think I've done some discussions on selective coordination here. Selective coordination is just the performance of overcurrent protected devices in a system. Selective coordination is not something that you're going to see a part of the product standard, if that makes sense. Crossover current, I don't even know what a crossover current is. Well, let's read it together. The current of a fused circuit breaker at which the function of the fuse coincides with the operation of the trip mechanism of the circuit breaker, where the fuse clearing time curve crosses the circuit breaker trip characteristic curve. Okay, I know, and now I know what it is. I know what they're saying. I never called it that in my life, but it is what it is. So crossover current, basically, there are some circuit breakers, and they call it a fused circuit breaker. I know there are some of my circuit breaker friends don't like to say it's a fused circuit breaker. They'll say it's a current limiter. But in any case, there are some circuit breakers where they'll marry a current limiting device, a current limiter, or a fuse to get the high interrupting ratings. So I'm relying on the molded case circuit breaker, or any circuit breaker, the circuit breaker itself, the contacts, to open on the lower fault currents, and I'm relying on the fuse for the higher fault currents. You'll see that, I know there are power circuit breakers that are designed with, say, 200,000 amp of an interrupting rating, and they get the interrupting rating at 200,000 amps because of the limiter or the fuse that's buried inside that device. Because that fuse is going to be doing the job and it's going to pick up. What I like about that is it gives you an indication. And Jason, you know about this from a 70E perspective. I know IBW and the Electrical Training Alliance educates on OSHA requirements. You've got to understand what type of fault was out there before you close it back in again. And just think, if you know that the circuit breaker opened for currents less than a certain number because currents greater than a certain number were cleared by the current limiting fuse, that those high fault currents provide the current limitation for the circuit, but also for the overcurrent device itself, for the circuit breaker and the assembly within which it's installed. So that current limiting nature of taking that current off very fast performs the function, but it gives you the awareness of what the magnitude of current that circuit breaker had to have seen. It's a ballpark figure, but hey, it's better than nothing, in my opinion. Don Kinnear says, and open on slate looks so much better than an enclosed panel board. Exactly right, Don. You could see the copper busts. It's pretty. Just don't touch it, right? Just don't touch it. And you know what? You're not supposed to. So you weren't supposed to misapply and interact with the product that way. Yes, Jason, you can't just turn it back on again. OSHA tells us we need to identify the problem and know why the fault happened before we close in. And when it comes to maintaining that overcurrent device, understanding the magnitude of current that it interrupted is another important piece of the puzzle. All right, so let's take a look. Current limiting circuit breaker. See, a current limiting circuit breaker is a circuit breaker that does not employ a fusible element. So that, and what we do there, let me tell you what we do there. I'll tell you what we do there. When we have a circuit breaker that is not current limiting, let me do this and do that and hit apply. When we have a circuit breaker that's not current limiting, you'll have a terminal like this, and let's say a terminal like this. And remember, you have two different types of contacts. You'll have a contact like that, where one has to open away from the other, right? And what we typically will achieve that with springs. The other way to do that, I don't know why I drew that like that. The other way to get this done, so let's draw the types of contacts. Right? Oh man, I'm getting good at this. So that's one type of contact. Another type of contact is to do this. And what that does, you think about the magnetic forces that are flowing, and and what happens with this type of a contact arrangement. You have the opposing forces wanting to push those contacts apart, and that's what creates, and that's the type of design that you'll see in a molded case circuit breaker that helps it become current limiting and in nature. There are other ways to get that done. That's just a really easy way to demonstrate a technique. And again, they give you some definition for what a current limiting device is, and it'll have to be marked as a current limiting device. It'll have a current limiting range, right? So the currents have to be high enough for you to get the current limiting nature of the clearing time. All right, so those are just some of the definitions. Now you'll see in here the definition of a molded case circuit breaker. A circuit breaker that is assembled as an integral unit in a supportive and enclosed housing. You'll notice nothing in here will say miniature circuit breaker. Nothing in here says residential circuit breaker. It's a molded case circuit breaker. It's listed to UL 49. You may put it in a panel board for a residential dwelling unit. It may be small. You may want to, the marketing of the manufacturer may call it a miniature circuit breaker, but that doesn't mean a hill of beans, okay? That's just a marketing way, and it's not a defined term. Insulated case circuit breaker, same deal. An insulated case circuit breaker is a molded case circuit breaker. And you're not going to find, I'm just going to do a quick search in here. No, I can't do search. You're not going to find an insulated case circuit breaker defined in this document. You're absolutely right, Jason. The protocol is often overlooked. Should be in bold letters on the cover of the ES Electrical Safety Program and on a bulletin board, yes, to prevent further damage, injury. Absolutely. Yep. All right, so let's move a little forward here. Okay, let's talk about the fact that remember we said the tripping of the automatic means of tripping a circuit breaker is going to be driven by the time current characteristic curve. The overload element, that top portion of the curve, is typically a bimetal. Typically, it's not always a bimetal. I may have an electronic trip unit in there, but it's typically a bimetal. And then the instantaneous region is either done by, I call it the clapper, right, where you have the two pieces of metal that are strategically separated by a distance, When you have very high fault currents, the magnetic forces, instead of propelling them apart, they pull them together. That drops the latch. Boom, it trips. But you need a very high current to get the magnetic forces. How high of a current will, from a mechanical nature perspective, will be determined by how far apart those plates are. I could also have an electronic trip unit that will give you the instantaneous performance, and that will be based upon a CT and a microprocessor telling the overcurrent device when to open. And when it tells the devices to open, it's going to be, it's a mechanical device. So it's springs, it's levers, all those great things that we all love as electrical professionals. We love springs and mechanical stuff, right? Not. All right, so specific purpose categories you might have. Okay, so this document, I'm going to go relatively quickly through this because I want to get to more of the application. You might have remotely operated circuit breakers, integrally fused. We already talked about those. We already talked about current limiting, switch duty. So now a switch duty circuit breakers. Let's see what they say about it here. They don't say much, but in for a switch duty circuit breakers marked SWD. Oh, they do. Here it is. That's what I was looking for. Fluorescent lighting loads on a regular basis. So when we see the reason they came up with SWD, they did a couple things in the testing in UL 489. They've given an extensive test on using it as a switch. That is basically the number of operations. The other thing they do is they adjust the power factor of the circuit that they are stopping the flow of current. Remember what power factor is. A power factor is the timing between the current waveform and the voltage waveform. It's either going to be, let's do this. When I say the separation or the timing, I'll have, ooh, that's a crooked line, isn't it? We'll do a white line for, I don't know, one of the two, and we have a sine wave that looks like this. And then you may have a sine wave that looks like this. Okay, boy, that was terrible. What we like is say the white line is your current. We like the zero crossings for current. That zero crossing is the time to open. Now I have zero current flowing and I can open. The challenge is when the voltage is maximum, so if my voltage was such that, if my voltage was such that the peak voltage was at the same time as the peak current, that's the hardest time to interrupt because I've got a lot of voltage and I've got a lot of current. So what you want the maximum voltage to be at zero crossing for current, if that makes sense, okay? So the power factor establishes the relationship between that voltage and current. And what we do is we test the circuit breaker at the specific, we call it the power factor of the circuit. And a fluorescent lighting presents a different power factor. So you'll see a couple things change. You'll see the power factor and you'll see the number of operations, the cycles on the handle. All right? We may have a motor circuit protector, which is an instantaneous only, and then the overload element is handled by the motor overload. You may have, now that's typically gone away. I believe, my gut's telling me that all of these UL 49 devices are hacker rated. I'm feeling confident that all of these things are hacker rated. Not everything is switch duty, but I believe everything is hacker rated. But I may be wrong. Look for the HACR to see if it's on the breaker. Then you have your marine circuit breakers. These aren't circuit breakers that get on a plane and fly off to other countries and fight wars. These are circuit breakers that are used on board a vessel, a boat, etc. They have to be put through different tests, especially around shaking and all that jazz. All right. And they have to meet the regulations of the U.S. Coast Guard. So you'll have marine circuit breakers. A marine circuit breaker may be designated as ignition protected. Ignition protected device is a device component constructed. So, but in any case, I'm not sure how many of you out there deal with that. I'm not going to spend too much time on it. Don, I was just reading Don Ganier's note. Don says, all breakers since sometime in the 90s meet the hacker, HACR requirements. I agree with you. I agree with you, Don. I think it's just part of the standard. I'd have to take a look back at the UL standard. I believe every one of these devices are adequate for that. Then you have your naval circuit breakers. You have your mining circuit breakers. High intensity discharge lighting. So if you're doing HID lighting, again, HID lighting is going to have a different power factor than your other types of lightings, and you want to make sure you test it with that power factor. So they're marked HID and they're rated 50 amps maximum and 480 volts or less. So we're following the code in that regard. You have your GFCI breakers, ground fault protection of equipment. So we talked about those. Classified circuit breakers. These are circuit breakers that are put through tests, again, in other manufacturers' assemblies. A very important thing to remember. I know I got kicked, I gotta love this one. I got kicked out of Lowe's one time because I was demonstrating the AFCI in the electrical aisle. And a person came in with a circuit breaker, and she said, she looked at the gentleman who was working the aisle and said, this breaker doesn't have any labels on it. And I was surprised. I didn't see any manufacturer on it at all. I don't know if it's just because it was that old or if it was worn. I don't know. It didn't have any labeling on it, which was very odd. Even in the plastic, it did have like interrupting ratings and things like that. It just didn't have the manufacturer's label on it. Didn't tell you what manufacturer it was. And you know what the gentleman said? Oh, just I'm not going to say the brands, but he said, well, just use this one. This one fits all of these panel boards. And it wasn't classified. And I made this statement. I said, oh, no, you can't do that. You need to find out what is the brand of the panel board that you have and make sure you buy the right breaker for that panel board. The individual was very happy and said, I'll be back. I live a short while away. And she was going to do that, but the manager of the store didn't like it, so lost the sale, I guess. But you have to make sure that the breaker matches the panel board, unless it's a classified breaker. And if it's a classified breaker, they'll tell you all of the panel boards that breaker was listed and tested in. All right, so that's the classified breaker program. Circuit breakers with secondary surge arrestor, so you can have surge in it. We already talked about that. TVSS. Oh, this is circuit breakers for use with uninterruptible power supplies. Steve says, Laurel, I know, Laurel, man, they are useful when the breaker enclosure ambient is far different than the rest of the circuit. Ah, okay. Excellent. And Laurel, yeah. Yep, that's was not one of my prouder moments, but I did stand up for safety, so I was happy. But I had to pack and leave. I had the walk of shame out the front door. So in any case, circuit breakers comply with the requirements of Supplement SC of UL 489 for uninterruptible power supplies. There's the AFCI circuit breakers that detects the arcing and sparking, that doesn't do shock protection, doesn't do the 489 nature of the device is the thermomagnetic, etc. But the AFCI just does arc protection. There's your look, you can get a 400 hertz rated circuit breaker. Look at that. We can list it for 400 hertz. I believe, and Dawn, you might know better than me, or you might be able to relate this, but I believe 400 hertz is common on aircrafts, like helicopters and things like that. I believe that's where we would see 400 hertz. Oh, 100% rated circuit breaker. Oh, I love these discussions. I love these discussions because I've heard people say, oh, remember, working your way into 100% rated equipment starts with the load calculation, right? And if you recall, when we do like an ampacity discussion, whether it be Article 215 or Article 210, I think it's 215.2 and 210.20, somewhere in there. They'll tell you that you have to do two calculations, one at 125% times the continuous, the other at, and not the conditions of use, the other with just the conditions of use. You pick the larger of the two. If you have a 100% rated circuit breaker and associated equipment, then I don't have to worry about the overcurrent device and the equipment being greater than 125% of the continuous current. I can use that equipment at the continuous current without doing the 125%. So what it does is it reduces the size. It reduces the size of a lot of stuff. But the issue that you have is you just can't take a 100% rated breaker and put it in any panel board. And I'm hoping that we say this here. The rules of the intent of the NEC permit the, 210.20, 215, I think it's .2 now. I'm not sure if it's maybe it's .3. Permit the overcurrent protector to be rated 100% rather than 80%, where, here it is, I love it, where the assembly, including the overcurrent devices, protecting the circuit is listed for operation at 100% of its rating. You'll find that in some cases the panel board or whatever it is, the equipment that you're putting it in, it could say you can't do this at 100%. Any aluminum bus panel board will never be 100% rated. That's a good dictate. It's a good easy checkbox. If they say, oh, look, I got a 100% rated breaker in there, and you open it up and it's got aluminum bus, violation, because you're going to need a copper bus, and in some cases you'll need high density copper, because remember, it's about the heat. Okay, it's about the heat that's generated because of the continuous current. That's why the heat is why when you look at a circuit, when you think about a circuit breaker, the 75 degree C column, we look at say it's a 75 degree C or a 60 degree C piece of equipment. We go to table 310.16, and whatever that value is for the size of a conductor that you're going to place on it, you can't go any higher in the overcurrent protection than that rating to provide the protection of the equipment. If I have a circuit breaker and I have the 75 degree C column says 200 amps, I can't exceed 200 amps for that circuit breaker. If it's 163 amps, I can't go to the 200 amp, I got to go to the 150 amp, because I can't exceed the number that's in the 75 degree C column, because I'll have too much current passing through the equipment, generating too much heat, okay? So we use the copper in the conductor to wick the heat away. If I put too small of a conductor on the lines and lugs of a overcurrent protected device outside of how it's tested, that would be ungood, all right? So unless it's 100% rated. Now, if it's 100% rated, now the equipment maybe, just maybe, the high density copper of the bus compensates for increasing the conductor size, right? Maybe, just maybe, the size of the enclosure getting larger compensates for the smaller conductor size on the lugs of that circuit breaker, right? So it's critical to understand this piece of the puzzle for the proper application of a circuit breaker. Typically, all of those are 80% rated. 1 over 0.8 is 1.25. So that's where the 1.25 comes from. All right? All right, but it's very important. You can't just go buy a 100% rated breaker and stick it into any panel board. The panel board has to say it is listed for 100% rating. Okay? And look, and I like this paragraph here. It helps you understand that they put it in the minimum size enclosure for the application of 100% of the breaker's continuous current rating. The circuit breakers may require 90 degree C cable size at 75 degree C ampacity and specific enclosure sizes and ventilation, right? So you may need the 90 degree C insulated cable, but you're going to use it at the 75 degree C. You can't use a 75 degree C insulated cable at 75 degree C. In some cases, follow the manufacturer's instructions. Don Kinnear says it was the 11th edition of the UL49 that made all listed breakers listed for 250 amps or less and 600. Okay, excellent. UL49, the 11th edition is what made that possible for us. And now I don't have to worry about looking for the HACR rating, the hacker rating. It's built in for 250 amps and less. So thanks, Dawn. Research, number one. You were the man. Okay. And I like the way it says here, UL 890, UL 67 switchboards tested to UL 891. All of these, you have to make sure that not just the breaker, but the assembly is listed that way. You've got PV circuit breakers. That's a 498 thing. Other applications. All right, so let's keep going down. Now, we know that a circuit breaker is going to have a frame. It may have an interchangeable trip unit, may not. You're going to have an operating mechanism. Each pole is going to be on each phase. You may have a pole where you're switching the neutral, if that's required in your application. You may have accessories. That's important to understand how those accessories get applied, right? And in some cases, you may have to take the circuit breaker apart to be able to put the accessory inside. These are all details. Follow manufacturer's instructions. Rear connected, mounting, stationary mount, plug-in mount. So in some cases, you'll have a plug-in, a plug-on, where you say, like typical residential, it slides over either a nub or a post, and the breaker will slide over top. There'll be a spring type of contact inside the breaker that slides over, say, a metal post. In some cases, it might just be a little nub. And then in other cases, those same miniature breakers in a commercial or an industrial type of panel board that's not typically installed in a residential pellet board application is bolted on. So you'll have a bolt on. It's important to understand the breaker has to mate with the bus that it's being mounted to. But you may also have a cable in, cable out, right? So you may have a circuit breaker that you land a cable in on one side and you put the cable on the other side, and you have two terminations. So understanding your application, working with a manufacturer of your choice, you can identify the appropriate termination points or methods for your application. If you have an existing panel board, go to the manufacturer of the panel board. If you have like an industrial control panel, You might have cable in, cable out inside of an industrial control panel. You may have in an industrial control panel a bolt-on, etc. All right? So you have the plug-in, you have the stationary, you have the draw-out. That's like a racking mechanism. I know various manufacturers have taken and what they typically will do for racking a molded case breaker in and out, they'll typically, I'm going on a limb, they'll typically, I don't want to say, I'm struggling with the word typically because typically means it's often. Some manufacturers will take their breaker and put it in a cartridge where they bolt it in, and the cartridge itself slides in and off the bus. It's not necessarily the breaker itself. Okay? So in fact, there are some manufacturers that might sell a separate unit that goes on the line side to facilitate the marriage of that overcurrent device with whatever assembly you're putting it in. So understanding the accessories, there are a lot of accessories that you can get for a circuit breaker. It's like buying a Jeep, for goodness sake. You know, you buy a Jeep and hey, I can put different wheels on it. I can lift it. I can put lights on the top. I can change my doors out. There's so many things you can do. Molded case circuit breakers, power circuit breakers, very similar. I can put electronic trip units. I can put shunt trip. I can put contacts so I know the state, etc. All kinds of stuff that you can do associated with that. All right, so shutter cell positions, handle orientation. All right, reverse feed. Okay, so if it's marked line and load, if it's marked line and load, line is line, load is load. Current flows from line to load. All right? Don't put it in a circuit where current is going to flow from load to line. That would not be in conformance with the standard. We went through this battle in Article 705 a few times over the last few cycles. It hadn't been as clear as it could be. I think the 2023 is pretty daggone good. 2026 is going to be even better, right? It's like a fine wine, gets better with time. All right, here you go. So ampere ratings, this information, and what we should do is add the 10 amps. So when we update this NEMA document, 240.6a was updated in the 2023 code cycle to add the 10 amp circuit to the list of standard ampere ratings for inverse time circuit breakers. And this list that you see in this is mimicked identically, maybe not in this form, but it is those breakers that are listed there are a part of 240.6 alpha. All right. Section 240.6b applies to adjustable trip circuit breakers and notes that the rating is the maximum setting possible, with an exception for 240.6c that the circuit breakers have a removable and sealable cover. So when you look at 240.6, it's going to tell you that if you have an adjustable trip unit, if you have a lock on it, that gives you various ways to meet the requirement. I could lock the door to the electrical room and say that breaker, because it's adjusted to, because it's, say, an 800 amp frame breaker that's been adjusted to 600 amps trip, that now that's a 600 amp circuit breaker because I have met the requirements in 240.6 where I either lock the cover, all those jazzes, password protected, and now it's a 600 amp breaker. I can put 600 amps worth of conductor on it, okay? You got voltage ratings. Be careful of the voltage ratings for the proper application of a circuit breaker. If it's slash rated versus straight rated. If it's slash rated, for example, if I have a 480/277, I can't use that on a 480 volt delta system, because the lower number tells you the maximum voltage line to ground or line to neutral that it can interrupt. And a circuit breaker that's, say, 480/277 put on a delta system, if there's a ground fault, the 277 number would be exceeded. So you would need in a delta system or a high leg grounded, right? You would need a straight rated 480 volt breaker. That way it can interrupt 480 volts regardless of the voltage potential between conductors or to ground. So understanding the voltage ratings for the proper application of a circuit breaker, muy importante. All right. Interrupting ratings. Remember, interrupting ratings are going to be voltage dependent. Make sure that, I don't know if is it D-E-N-T or D-A-N-T? Dependent. Dependent? A dependent is an individual. Dependent, I think, is E-N-T. But in any case, you get my drift. I may have a breaker. I may have a circuit breaker that at say, at 240 volts, I can interrupt 25,000 amps. At 480 volts, I can only interrupt 10,000 amps. Okay? The higher the voltage, the lower the interrupting rating will be. And make sure that when you're looking at the interrupting ratings for a circuit breaker, you pick one that will be applied, whatever voltage it will be applied at, that's the you have that interrupting rating not exceeded. Yes, thank you, Jason. Yep. A lot of people miss the 10 amp OCPD, and there are cases for small motors that will require the use of the 10 amp breaker based on 430.52. Absolutely. A 10 amp molded case circuit breaker is out there. So the only thing you're not going to get is a 10 amp GFCI or a 10 amp AFCI. I don't know. I don't believe any manufacturer is making those, but a 10 amp molded case circuit breaker, perfectly suitable and available on the market, readily available on the market. All right, we already talked a little bit about frequency. There's your 50, 60 hertz. Already talked about that. We already said if you have 400 hertz, consult the manufacturer, look for a 400 hertz breaker. Power factor config. Okay, this big misapplication. Let me couch that. Not a big misapplication. An opportunity for a misapplication in some instances. I don't want to overinflate the likelihood here. But keep in mind, now when we say X to R ratio, an X to R ratio is impedance of X divided by resistance. Now, R. So when you think about a circuit, when I think about, I don't like red, I like white. When I think about a circuit like this, okay, I come down to another breaker, and I come down to another breaker. Okay, and let's say I have a transformer up here. Okay, this is a conductor. This is a conductor. This is a conductor. Transformers, X is huge, high X. Conductors, if you look at the table, you're going to have an R plus a JX, and the R is not insignificant, okay? So when I get close to the transformer, my X to R ratio will be high because a lot of X is there in relationship. As I go down in the system, the R's add up. And my X to R, my R starts to encroach higher, so my total X to R will go down as I get further down in the system. So when I am close to a transformer, I have a higher X. In those cases, I could have I could have a circuit breaker that has a high X to R ratio. And what this tells you, here we go, look at this. Power factor or X to R ratio. So, and look at this is short circuit multiplying. Let's find 1.0. Here is 1.0. Here is 1.0. And here is 1.0. Okay? So, this is the short circuit multiplying factor. So for a power factor of, so this is for over 20,000 amps. For a power factor of 20%, my multiplier is unity for over 20,000 amps. For 10,000 to 20,000 amps, my multiplier is 1.11. For 10,000 amps and less, my multiplier is 1.31. What does that mean? That means that I will have to, when I say a 20% power factor, if I had 10,000 amps of a voltage fault current value, I have to multiply that by 1.31. That is what the circuit breaker should be tested for to be able to ensure that it can interrupt a 10,000 amp voltage fault current value when the power factor is 20%. That's a pretty low power factor, right? You want to be as close to unity. We're typically around 80%, right? So, but this is how the units are tested. So available short circuit count, so test circuits with lagging power factor, if it's 10,000 amps, we'll use 50% power factor. That means this is the setup. We'll use 50% power factor for those currents for 10,000 amps or less. We use 30% for 10,000 to 20,000, and for over 20,000 we use 20%. So, and that's where those unity are. So we set the system up for what we feel is the worst case scenario, for the worst case waveform separation. So when you're applying a circuit breaker, you've got to make sure that your power factor is within those limits, because if it's not within those limits on how we tested it, then you're misapplying the product, and you may have to adjust the interrupting rating of the circuit breaker. So what a program like SKM System Analysis or EDSA, Easy Power, all of those different types of software applications will give you an X to R ratio, and you got to make sure that your X to R ratio isn't too high such that it's outside of how the circuit breaker was tested. And I'm at 1:05. I am 5 minutes late for my next meeting. So I really appreciate everybody hanging in there. Thank you, Laurel. I really appreciate it. Jason Doty, thank you. Great topic. Smash that like button, hit that thumbs up. And if you're not subscribed to the YouTube channel, please make sure you do so. Thank you a lot, Steve, about the 100% and power factor calibrated MCCBs are important, but some in the field need to be aware of. Yes, I agree with you. All right, guys, I've got to run to another meeting. Thank you. Take care. Stay safe. And please, by all means, stay healthy. See you next week.